Hi there. Today I'll be talking about population models. Population models are mathematical models applied to population dynamics. These can help ecologists with population management and conservation. There are three main types of population models: geometric, exponential, and logistic. But these are not the only ways that populations can be modeled. I will also be discussing the concepts of life tables and metapopulation models. The first model I will be discussing is geometric growth. Geometric growth can be written as n sub t plus 1 equals lambda times n sub t, where n is the number of individuals in the population and t is the time or generation that the population is in, and the lambda is the finite rate of increase of this population. This can also be written as n sub t equals lambda raised to the power t times n naught, where n naught is the initial population. This is a graph of geometric growth, with time on the x-axis and the population size on the y-axis. As you can see, it increases in discrete time points in a J-shaped curve. The next model I will be discussing is exponential growth. Exponential growth can be written as dn over dt equals r times n, where n is still the number of individuals in the population and r is the intrinsic rate of increase of the population. dn dt is the rate of change of the population size over time. This can also be written as n sub t equals n sub naught times e to the rt, which is similar to the geometric growth equation, but rather than lambda to the t, we have e to the rt. This is a graph of exponential growth, again with time on the x-axis and population size on the y-axis. This is similar to geometric growth as they are both J-shaped curves, but in this case, the points can be connected to form a smooth line. This is because geometric growth is the population size measured at discrete time points, whereas exponential growth is a measure of the rate of change of population over time. Within exponential growth is the concept of doubling time, or the time it takes for the population to reach double its size as it initially was. This is written as t sub d equals ln2 over r. This equation is derived from the exponential growth equation, where n sub t is set to 2n naught and you solve for t. The next model I will be discussing is logistic growth. Logistic growth can be written as dn over dt equals r times n parentheses 1 minus n over k, where k is the carrying capacity of the environment, n is the number of individuals in the population, r is the intrinsic rate of increase of the population, and dn over dt is the rate of change of the population. This can also be written as n sub t equals k over 1 plus parentheses k minus n naught over n naught times e to the negative rt. This is a graph of logistic growth, once again with time on the x-axis and population size on the y-axis. Instead of the J-shaped curve we saw with geometric and exponential growth, here we see a more S-shaped curve. This curve approaches this asymptote, representing the carrying capacity of the population. The population grows towards this point, but does not pass it, where the population would not be able to sustain itself in its current environment. Next is the concept of life tables. Life tables commonly include the age or stage, denoted as x, the number of individuals in each age, which is denoted n sub x, the number of offspring, n sub x offspring, the survivorship or number of individuals which survive to the next age class, denoted L sub x, and fecundity or the number of offspring produced per individual surviving, or F sub x. Age or stage, number of individuals, and number of offspring can all be counted. However, survivorship must be calculated by doing n sub x over n sub 0, and fecundity must be calculated by doing n sub x offspring over n sub x. Using survivorship and fecundity, we can calculate capital R sub 0, or net reproductive rate of the population, which is just the sum of all of the fecundity values multiplied by the survivorship values. From this value for net reproductive rate, we can calculate capital G, or the generation time of the population. Capital G is equal to the sum of X times survivorship times fecundity all over capital R sub 0, our net reproduction rate. From these values of G and capital R sub 0, we can calculate little r, or our intrinsic rate of increase of the population. Little r is equal to the natural log of capital R sub 0 over G, our generation time. The last topic is metapopulations. A metapopulation is a group of geographically isolated populations which are linked together by dispersal. Each metapopulation is said to inhabit a piece of land called a patch. These can be modeled with the equation dp over dt equals cp times 1 minus p minus ep, where dp dt is the proportion of patches which are inhabited, c is the colonization rate of patches, and e is the extinction rate of patches. I hope this video improved your understanding of population models. Thanks for watching!